Thank you for standing by. My name is Tina, and I will be your conference operator today. At this time, I would like to welcome everyone to the Janux Therapeutics R&D Day. All lines have been placed on mute to prevent any background noise. Thank you. I would now like to turn the conference over to Andy Meyer, Chief Business Officer.
Thank you, operator, and good afternoon, everyone. Today, Janux issued a press release highlighting pipeline progress and the best-in-class potential of a novel bispecific platform for autoimmune diseases. This press release, today's webcast, and corresponding slides will be available on our website. Before we begin our prepared remarks, we would like to remind everyone that certain comments made by Janux management on this call will include forward-looking statements. These forward-looking statements are based on current information, assumptions, and expectations that are subject to change and involve a number of risks and uncertainties that may cause actual results to differ materially from those contained in such statements. These and other risks and uncertainties are described in our periodic filings made with the SEC. You are cautioned not to place undue reliance on our forward-looking statements, and the company disclaims any obligation to update those statements. With that, I would like to turn the call over to David Campbell, President and CEO of Janux.
Thank you, Andy. Today, I'm going to share with you our next tier of clinical programs via our very first R&D Day. I will be joined by Tommy DiRaimondo, our CSO and a fellow co-founder of Janux, to share these programs with you. At a top level, these programs are going to join our lead clinical assets, which we've spoken about previously, Janux 007 for prostate cancer, 008 for a number of solid tumor settings. Those will be subjects of their own individual updates later this year. Today, we're going to focus upon our development pipeline, where we're going to share with you 3 new programs that we're going to go into additional detail in the following slides. Our existing cash position at this point, we're well capitalized, slightly more than $1 billion in capital as of March 2025, enough to get to important pivotal data on 007 and early proof of concept data on our other programs, 008, and these programs that we'll describe today. Going into a summary overview of these 3 new programs. So the first that we're going to discuss is a PSMA CD28 tumor-activated tracer program. We're developing this to be used in combination with Janux 007, our tractor for prostate cancer, to further differentiate the depth and durability of patient responses. I want to be very clear here. We view this as an exciting opportunity where we are effectively doubling down on our Janux 007. We view the emerging Janux 007 data that we've shared with everyone, both with respect to the combination of safety and efficacy, makes it a compelling opportunity in prostate cancer. We're enthusiastic about its potential moving forward. This is an opportunity to further differentiate Janux 007 from other drugs being developed in this space. Next, we're going to talk about our TROP2 tractor program. This is building upon our clinical learnings from our first 2 tractor programs, 007 and 008, that are both in the clinic. Learnings from those have been rolled into this program. We also view the clinical data that we generated allows us to understand what's important as we develop these, and we felt it was time to initiate our 3rd tractor program using our underlying tractor technology program that's going to provide a very large market opportunity looking at the number of solid tumor indications that this target has been implicated in. And then 3rd, we're going to end on what we call a CD19 ARM program. As you could imagine, we've developed significant non-clinical and clinical expertise and understanding of T-cell engagers in humans as well as non-clinically. We've used this information to redesign bispecific T-cell engagers to have a best-in-class opportunity with respect to depth, durability of response with a very manageable reduced CRS profile that it's going to allow us to extend our pipeline into autoimmune disease. So we're going to go into greater detail in all 3 of these programs in the ensuing slides. The new programs join our existing clinical assets, 007 and 008, as well as Merck has two partnered programs that are undisclosed at this point that are also moving forward. So with this, we feel we have a robust platform, robust number of opportunities to create value around this platform. And many of you may be wondering why the R&D Day update now. You're going to be seeing clinicaltrials.gov and other public notifications on these new 3 programs over the next 3, 6, 9, 12 months. We felt at this point, giving you an opportunity to understand what they are, why we're pursuing them, was an important trigger for today's meeting. Just to remind everybody on this slide, we develop tumor-activated drugs where we identify peptide masks in red and purple. Those block the ability to interact with target. We also attach a half-life extender in blue. So we've got a tractor on the far left, protected. When it goes into healthy tissue, those masks block interaction with healthy tissue and T cells, so you're not driving pharmacology. The half-life extender gives you a nice long PK profile. However, upon entry into a tumor proteases cleave those linkers, release the mass and the half-life extender, giving you the bispecific. The bispecific is then able to drive full tumor pharmacology. I'm showing this for a tractor. The bispecific CD28 is simply change the T cell binding domain from CD3 to CD28 to generate its own mask, and everything else is the same. So a very modular approach that leverages our learnings from tractor, uses the same linkers, mass, half-life extender, really to begin to leverage the observations that we've gained with 07 and 08 in the clinic. So with that, I'm going to hand off to Tommy, who's going to walk us through our first 2 programs, starting with the PSMA CD28 tracer program.
Thank you, David. My name is Tommy D'Armando, co-founder and chief scientific officer at Janux, and today I'm going to share with you some exciting programs coming from the creative minds at Janux that really highlight our ability as a company to redefine the cutting edge of T-cell engager technologies, push the boundaries of what T-cell engagers can achieve, with the ultimate goal of helping patients live better lives. Now, the first program I'll discuss today centers on our tumor-activated immunomodulator or tracer platform, where an intention of this platform has been to combine with our tumor-activated T-cell engager or tractor platform, where this combination of tractor plus tracer is designed to enhance and prolong the anti-tumor T-cell response. Next. With that in mind, the first tracer molecule that Janux is moving to the clinic is one that builds on the back of our already compelling, differentiated asset that has exhibited unprecedented PSA decline, robust clinical activity with a well-tolerated safety profile in prostate cancer, Janux 007. What we rolled out in December of last year, shown in the upper table, really raised the bar across the field of late-stage mCRPC treatments, where we showed strong PSA responses of 100% PSA 50s, 63% PSA 90s, where a significant number of those patients maintained their response for 12 weeks or longer. In addition, we reported a competitive PFS and ORR in heavily treated population, median 5th line. So building on the shoulders of Janux 007 with its exciting activity profile, we see an opportunity to make it even better, to raise the bar yet again in prostate cancer. And to do this, we're planning to combine Janux 007 with a PSMA CD28 tracer that our preclinical data suggests may enhance durability and potentially prolong clinical responses. We also see it as a broader opportunity to strengthen Janux's emerging prostate cancer portfolio, and we're taking full advantage of that opportunity. Next. The masked PSMA CD28 molecule will be the first Janux tracer to move to the clinic. And the reason for that is it fits well within our strategic focus to potentially generate proof of concept early. First and foremost, what we know in prostate cancer is that Janux 007's clinical results are consistent with the design principles of our tumor-activated platform. What this translates to and why it's important is that these very same design principles are also engineered into our PSMA tracer, allowing us to draw analogies to the profile we observe with 007. Second, we see 007 as an ideal combination agent, given its predictable, dose-dependent clinical activity, which will serve as a solid foundation to develop the combination. Lastly, from our own clinical study with 007 and from our Regeneron study using their non-masked PSMA CD28 molecule, we've learned that mCRPC is both a tractor and PSMA CD28 responsive tumor type. Between that and our development expertise in prostate cancer, we see an opportunity to rapidly generate proof of concept for our tracer platform in the clinical setting and further differentiate Janux in the prostate cancer treatment landscape. Next, when it comes to the scientific rationale of why we see value in our tracer platform, at the core is the concept of CD28 co-stimulation, potentially enhancing the duration of our tractor activity and improving the related T-cell immune response against the tumor. The idea is that when the tractor enters the tumor microenvironment, gets cleaved and forms a bridge between PSMA on tumor cells and CD3 on T cells, this immunological synapse provides the tumor recognition element to the T cells, leading to their T cell activation. This is called signal 1 and drives T cell mediated tumor cell killing. Now add in tracer and the identical mechanism described for the tractor, but instead, the underlying bispecific forms a bridge between PSMA on tumor cells and CD28 on T cells. Another synapse, only this time it provides a co-stimulatory signal to the T cells called signal 2. This co-stim signal 2 promotes T cell survival and expansion, leading to stronger T cell fitness, important for more durable T cell responses against the tumor. Another factor is that the benefit of signal 2 requires the presence of signal 1, which aligns with our rationale for combining tractor and tracer. Next, the Janux approach of combining tractor and tracer platforms offers competitive advantages that differentiate from alternative approaches. A key aspect to the platforms is masking and, of course, tumor-activated designs, where we believe masking may even be required for this combination approach to be successful, based on multiple examples of non-masked assets that have gone before us and exhibited toxicity in humans. Two examples of non-masked assets in the upper right-hand box highlight why masking is important. First, Regeneron 5678, a non-masked PSMA CD28 compound that, although demonstrated efficacy, it also induced severe toxicity, including prevalent high-grade AEs with 2 grade 5 events. The other example is the tri-specific HER2 molecule from Sanofi that exhibited multiple dose-limiting toxicities, including cardiac failure, that may be consistent with HER2 expression in the heart, as well as grade 4 elevations in transaminases. Now, the toxicities with the Sanofi compound came without any objective responses, highlighting the struggle for these non-masked assets to get into efficacious doses in the absence of toxicities. By comparison, trispecifics now in the lower right box are limited by their design. Intramolecular stoichiometry constraints of each of the 3 binding domains, whether it's 1-to-1-to-1, 1-to-2-to-1, 1-to-1-to-2, or other options, it may not match the stoichiometries and geometries required for optimal T cell activation and durability. Another is there are 2 T cell binding domains within the same molecule now, CD3 and CD28, that if bind and trans across 2 separate T cells, for example, could induce T cell fratricide and potentially hinder efficacy. And lastly, trispecifics inherently can't vary the timing or dose level of the individual components, CD3 from CD28, that Janux believes may be important to achieve best clinical outcomes. Altogether, the Janux tractor and tracer combination approach has strong competitive advantages with best-in-class safety and efficacy potential. Next, onto the data that highlights the design principles of our PSMA tracer, where its activity depends on a few things: the presence of signal 1, concentration, and protease cleavage. So on the left-hand side, we show dependence on signal 1 using an in vitro prostate tumor cell killing assay. We show in blue that our non-masked PSMA CD28 T-cell immunomodulator, or what we call TCI, lacks activity as a single agent due to the absence of signal 1. However, when we provided that signal 1 to the system using a low-level PSMA CD3 T-cell engager now at its EC20, shown in the red bar, combination with that using the PSMA CD28 completely killed all the tumor cells in the system, shown in green. Now, on the right-hand side, we show dose and cleavage-dependent activity of the PSMA tracer. And in the red curve, our masked PSMA tracer exhibits largely attenuated tumor cell killing potency compared to the non-masked PSMA CD28 in blue. But cleavage of the PSMA tracer with protease, shown in green, completely restores full functional activity, a property, of course, entirely consistent with the desired function of the molecule, where we have reduced activity in healthy tissue when the masks remain in place, but full activity in the tumor microenvironment where the masks are released due to cleavage by tumor-specific proteases. From this data, we are confident that our PSMA tracer can enhance the activity of our PSMA tractor in combination. Next. Now, another important aspect of our tracer platform is the ability to improve T-cell fitness and extend duration of tractor-mediated tumor killing. What we did to assess this was devise a T-cell durability assay shown in the left-hand side of the slide, where we co-culture T-cells and prostate cancer cells and repeatedly challenge those T-cells over and over again with more cancer cells in a method designed to rapidly induce T-cell exhaustion. Based on these types of assays and clinical data published by others, we expected attenuated T-cell function over time using T-cell engagers. In fact, both Amgen and J&J have published on their own T-cell engagers where they showed loss in T-cell function during dosing and upon disease progression in their oncology trials. Now, on the right-hand side is our data. In blue is the single-agent PSMA CD3 T-cell engager that, similar to expectations, lost tumor control due to attenuated T-cell function around day 10 to 15, soon after the third addition of the tumor cells. In red, we show that the combination of PSMA CD3 with the PSMA CD28 maintained tumor cell killing for greater than 50 days in 9 repeat cycles of prostate tumor cell killing. We also tested whether delayed addition of the PSMA CD28 molecule could rescue tumor cell killing after attenuation of T-cell function had already begun, and we show that in the green curve. So just following that green curve along on the right-hand side of the figure, we first have 2 cycles occurring between days 0 and 10 that are single-agent PSMA CD3. At day 10, the combination with the CD28 molecule starts, and you can see that although tumor growth occurs for several days post that combination, the T cells are able to regain tumor control around day 15 to 20, where tumor cell killing is apparent as the green curve is steeply moving downward and tumor cell density is declining. Importantly, thereafter, full tumor cell killing progressed in this group for the remainder of the experiment. This data really highlights the power of the combination to enhance T-cell durability and supports our plans to combine PSMA tractor and PSMA tracer in prostate cancer patients and potentially further differentiate our prostate cancer portfolio. Next. Moving to our non-human primate studies, we have tested our masked PSMA tracer as either a single agent or in combination with an active dose of a PSMA tractor. Building off previous non-human primate studies where we tested our non-masked T-cell engager and observed clear cytokine release, elevation of liver enzymes. In contrast, reduced cytokine release with normal pathology ranges were observed with our PSMA tractor. We then used this information to define a high and active dose of the PSMA tractor based on T-cell activation, cytokine profiles, and combined that tractor in dosing with the PSMA tracer. Importantly, in the cynos, relative to the single-agent PSMA tractor at a high dose shown in purple, we did not observe increased cytokine release. We had no adverse clinical signs or any observable healthy tissue toxicities from the combination shown in the green, where we added the PSMA tracer on top of the tractor. This data highlights the masking is working as intended and the ability to safely administer the combination. Now, the single-agent tracer shown in red had no clinical signs and minimal cytokine release, as we would expect. These animals don't have a signal 1, so providing the signal 2 had no impact, similar to what we saw in vitro. Now, given the PK exposures shown in the middle panel, we conclude that the large safety window of that combination potentially enables dosing in the clinic well above the anticipated human efficacious dose. Next. For this program, our PSMA tracer is currently in IND-enabling studies, shown in the left-hand box, where we anticipate filing the IND in the first half of next year. Following that IND, we anticipate dosing patients in the second half of next year, with plans to understand PK safety, efficacy, and importantly, durability as we hunt for our preferred dosing regimen. Importantly, our clinical experience with Janux 007 will guide our dosing strategies for the planned combination. And that repeat tumor challenge assay that I showed you earlier really supports flexible timing of when we can combine PSMA tracer with Janux 007 that we're thinking about as a means to potentially optimize patient outcomes. Given our experience and expertise in prostate cancer from 007, we expect to accelerate our PSMA tracer proof of concept. Next. Ultimately, our PSMA tracer program is an exciting opportunity for Janux, where we plan to leverage our potentially best-in-class asset, JANX007, and raise the bar yet again in prostate cancer through combination with our PSMA tracer. With our strong non-clinical data sets that demonstrate enhanced durability in vitro and a large safety window in primates, we anticipate prolonged duration of responses through potentially safe administration of JANX007 and PSMA tracer in combination for prostate cancer. We further recognize that prostate cancer is both a PSMA tractor and PSMA CD28 responsive tumor type that's conceptually attractive for our tumor-activated approach, again, designed to reduce CRS, reduce healthy tissue tox that may otherwise accompany analogous non-masked approaches. And finally, I'll wrap up by acknowledging our JANX007 experience may facilitate accelerated clinical development and potentially enable a rapid proof of concept for our tracer platform with anticipated patient dosing in the second half of next year. Next. Moving to our second program for today is an asset advancing within our tumor-activated T-cell engager or tractor platform that targets TROP2. Next. Now, what Janux sees in targeting TROP2 is opportunity for a potential first-in-class TROP2 T-cell engager with competitive advantages that differentiate our approach from others. First, Janux has tractor molecules in the clinic, and learnings from these assets, 007, 008, give us invaluable insight on how best to apply these learnings to our TROP2 program. And second, what this enables us to do is potentially accelerate development in areas where TROP2 targeted agents have had success, for example, antibody drug conjugates or ADCs. However, even though TROP2 ADCs have demonstrated clinical success, there is room for improvement, in our opinion. For example, Trodelvy exhibited 73% grade 3 and above AEs, along with reduced activity in low TROP2 expressing tumors. In contrast, through masking and tumor activation, our tractors are specifically designed to improve safety, to drive high doses and increase intratumoral concentrations of the active drug, a potential consequence of which is stronger efficacy. Now, our analysis on TROP2 suggests it is widely expressed across multiple tumor types with high unmet need, where upwards of 400,000 patients are receiving second-line plus therapies across the US and EU on an annual basis that we estimate represents a multi-billion-dollar market potential. And therefore, we see TROP2 as a potentially high-value asset that may enable access to new indications and expand the breadth of patients we can treat across our portfolio. Next. Of course, accessing TROP2 as a target in solid tumors using T-cell engagers, we believe, critically relies on Janux technology, masking tumor activation. On the left-hand side of the slide, we are showing that TROP2 is broadly expressed in healthy tissue, skin, kidney, bladder, liver, pancreas, and others, that in the absence of masking potentially limits contemporary TCEs due to substantial dose-limiting toxicity risk. In contrast now, our tractor approach, shown on the right, utilizes masking designed to block target engagement and activity in healthy tissue. In addition, cleavage-dependent activation of the tractor coming from tumor-specific proteases is designed to focus its activity to the tumor microenvironment. These features built into the TROP2 tractor are really designed to reduce CRS, healthy tissue toxicities, and address key limitations of conventional T-cell engagers. Next. When it comes to our data, we've run in vitro and in vivo experiments that highlight the large activity and safety window of our TROP2 tractor development compound. And here we're showing tumor cell killing in vitro using tumor cells plus human T cells in a co-culture assay, where the red curves are our TROP2 tractor, the blue curves are the non-masked TROP2 T cell engager, and the green curves are protease-treated TROP2 tractor. And what we can clearly see is tractor in red exhibits a dose and cleavage-dependent activity consistent with its design. For example, the red curves from the tractor show higher concentrations are required to observe tumor cell killing compared to the enzymatically cleaved tractor in green or the non-masked T-cell engager in blue. Although we've tested many different cell lines in our assays, the cell lines shown here also highlight activity across a wide range of tumor types and, importantly, target expression densities, where we observe full tumor cell killing even at low TROP2 expression densities, indicating to us an opportunity to treat tumors across the full range of TROP2 expression, as well as a breadth of responding tumor types with high unmet need. Next. Complementing our in vitro results, we also tested our TROP2 tractor in vivo in a stringent tumor model where TROP2 expression is low, and compared that to data published for TROP2 ADCs. We utilized the model of triple-negative breast cancer, where human PBMC engrafted mice bearing MDA-MB231 tumors were treated with the non-masked TROP2 T-cell engager in blue, the tractor in red, a non-cleavable tractor in green or vehicle in black, shown on the left-hand side of the slide. While the vehicle and non-cleavable treatment groups exhibited rapid tumor growth over the study, the tractor and T-cell engager demonstrated anti-tumor activity and tumor shrinkage. The difference in activity of the non-cleavable versus the cleavable tractor at the same dose level of 1.5 milligrams per kilogram highlights that the in vivo activity is cleavage dependent. This activity also drove a clear survival benefit in the mice, shown in the Kaplan-Meier plots in the center left panel. Moving to the right-hand side of the slide, by comparison, ADCs are not active in these low TROP2 expression models, indicating their TROP2 expression threshold for activity is higher than that required for tractor. First, Trodelvy was tested in the MDA-MB231 model, similar to Janux, and did not show significant tumor growth inhibition even at doses of 25 milligrams per kilogram. Likewise, Datroway tested a number of patient-derived tumor xenografts in mice and found a clear TROP2 expression correlation, where patients' tumors with low TROP2 expression based on immunohistochemistry scores of less than 100 were not responsive. Together, our preclinical data support TROP2 tractor's anti-tumor activity, even at low TROP2 expression densities, that clearly differentiates from TROP2 ADCs. Next. Consistent with preclinical models, outcomes now in TROP2 ADC-treated triple-negative breast cancer patients also depends on TROP2 expression in their tumors. A publication summarizing the late-stage clinical evaluation of Trodelvy clearly showed that patient responses deteriorated if the tumor TROP2 expression was low. The table shown in the middle summarizes clinical results from Trodelvy's phase 3 ASCENT trial in triple-negative breast cancer. And what they did is break down their data sets into quartiles based on TROP2 expression levels measured by immunohistochemistry that they quantified using H-scores. So what you can see is that low, medium, high, and very high each have their own H-score range, and each represent 25% of their patients. Now, they also kindly provided a sub-analysis of the bottom quartile or low quartile, where they looked at patients with an H-score of less than 50, therefore very low TROP2 expression. And what you can see across these patient groupings is that when it comes to efficacy measured by PFS, OS, and ORR, that weaker efficacy correlated with lower TROP2 expression. Additionally, in the very low TROP2 H-score group, you'll notice further reduced responses to Trodelvy, and in the low TROP2 H-score group, minimal improvement in PFS and OS over the physician's choice group. Based on these clinical results and our preclinical data, what we see is an opportunity to come in with our TROP2 tractor and potentially improve efficacy where patients may derive limited benefit from an ADC due to low TROP2 expression in their tumors. Next. We next progressed to non-human primate studies with our TROP2 tractor and compared it to our non-masked version, the TROP2 T-cell engager, both of which are fully cyno cross-reactive. What we observed is that while our TROP2 tractor was well tolerated with no adverse clinical findings consistent with a lack of measurable healthy tissue tox, the TROP2 T-cell engager, on the other hand, was quite active at low exposures and induced clear signs of CRS, including fever, neurological effects, as well as clear signs of healthy tissue tox in the GI tract, skin, and kidney that are all TROP2 expressing tissues. This potentially reinforces that TROP2 may not be an accessible target for contemporary TCEs, just given this tox profile. Importantly, as shown in the middle panel, we were able to achieve a TROP2 tractor exposure greater than 5,000-fold higher than the maximum tolerated exposure of the non-masked T-cell engager and still have room to dose higher due to a lack of adverse events that we tested in this study. At the far right, we show cytokine induction of the tractor is low, which is consistent with a lack of CRS where no fever or other signs were observed. One last important point to make is based upon learnings from 007 and 008 in the clinic. These safe and well-tolerated exposures that we see here in monkey for our TROP2 tractor are likely well above the anticipated efficacious doses in humans. Therefore, based on the large safety window in primate, we anticipate the ability to increase dose, drive higher intratumoral concentrations of our activated drug for potentially stronger efficacy in patients. Next. Tying it all together, Janux is well positioned to access high-value targets like TROP2 using our tractor platform. With the tractor platform comes the ability to mask, again designed to reduce CRS and healthy tissue tox, strongly supported in the case of our TROP2 by non-clinical studies in monkey where we achieved a large safety multiple with exposures far above the anticipated human efficacious doses. We also demonstrated that our TROP2 tractor is active in vitro and in vivo across a broad range of tumor types and all levels of TROP2 expression, including low TROP2 densities that clearly differentiates from ADCs and affords us the opportunity to potentially provide stronger benefit to patients that may otherwise derive limited benefit from ADCs due to low TROP2 expression in their tumors. Given the wide range of tumor types that express TROP2, Janux has the opportunity to add new indications with unmet need into our portfolio. In addition, the invaluable learnings from our ongoing clinical programs 007 and 008 will help accelerate our development path, potentially generating TROP2 tractor proof of concept earlier. As of now, we are embarking on IND-enabling studies this year and are excited to bring another tractor to the clinic and seize the opportunity for a potentially first-in-class TROP2 tractor that differentiates from ADCs. And with that, I'll pass it back over to David.
Thank you for that thorough overview, Tommy. Appreciate it. At this point, I'm now going to take over and walk you through a new platform, a new approach that we call an adaptive immune response modulator, or ARM platform. The way to think about these are they're simply redesigned bispecific T-cell engagers. There's no co-stim, nothing added. What I'm going to walk you through is our approach and the data that we think clearly differentiates the ARM from contemporary T-cell engagers. So, as you can tell, we've generated a lot of information over the last few years, both non-clinically and clinically, about the performance of T-cell engagers, ways to improve them. And we applied all of that as we started thinking about, are there other approaches that we could take beyond simply combining with CD28? And so on the left-hand side of this slide, if you look at contemporary T-cell engagers, we've seen very good efficacy, seen very nice response rates and durability. The only reason they're light green is we've learned from our 007 program, if you can deliver more active drug to the tumor and spare healthy tissue and CRS issues, you have an opportunity to further increase response rates and depth and durability compared to contemporary T-cell engagers. And then other limitations, CRS requiring inpatient treatment, healthy tissue toxin infections have all been noted in the public domain. Our ARMs, I'm going to share with you a range of different data sets. We maintain comparable efficacy that leads to improvements in response rates and durability. CRS is very limited. We're viewing this as an outpatient potential. We can combine with tractor for healthy tissue tox, and we believe the profile that with T-cell activity that we're showing, we should have an improvement in infection profiles. So these were the underlying thoughts as we embarked on this approach a while back. Where we started is we looked at the typical immune response in cancer patients shown on the upper left-hand side. Beginning on the left-hand side of that, first you have foreign antigen presentation, and then what you get is this robust T-cell expansion of different T-cell subsets that we summarize on the bottom, leading in the end to an increase in the number of effector cells shown in red. And the effector cells are, of course, the actual T-cells that do the majority of the anti-tumor killing. So looking in the green box, there's a similar characteristic in good responses, both in patients who clear their tumors on their own and patients who are checkpoint antibody responders, as well as CAR T responders. And the one thing they all have in common is they have this robust T cell expansion that continues to support the effector population to drive a significant, deep, and durable anti-tumor response. I want to spend just a minute or so on the T cell subsets below. Go from left to right. You start with naive, you go through the memory populations in green, and then finally you get to the effector populations. And as you go from left to right, what occurs a few things. On the left, you've got a very long lifespan. On the right, with the effector cells, part of the challenge is that they have a very short lifetime. On the left-hand cells are able to differentiate. And what that means, naive can convert to transitional memory, can convert to central, can convert to effector. And by the time you get to effector, you're terminally differentiated. The other aspect on the left-hand side is you have this increased self-renewal and expansion. So basically, with the right stimulation, each of these populations on the left can expand significantly. Effector populations on the right can't do that. The effector populations, of course, are absolutely critical. They're the ones that actually perform the anti-tumor activity. They drive cytotoxicity. They're also the major source of the inflammatory cytokines, TNF alpha, interferon gamma, as well as granzyme B. So you have this, we view the left-hand side, really we view them as the expansion leads to a reservoir of these cell types, these memory cell types, that can continually replenish the red effector population. Because remember, the red effector population is doing the anti-tumor activity, but due to its short lifetime, they're turned over rapidly. So they need to be continually replaced. As we look at patients on this slide on the bottom that have an ineffective immune response, either with progressing tumors or in the papers that we refer to up above, the checkpoint antibody non-responders or the CAR T non-responders, what you see a constant trait in these patients is you do not have that robust T cell expansion. You have a minimal T cell expansion of these memory populations. So basically, you're relying on the existing red effector population. You have minimal opportunity to replace them due to their short half-life. If you have enough of them upon treatment, you have an opportunity to have a good anti-tumor effect. If you don't have enough of them, your response is going to be limited by this small effector population. So a key difference that we notice in responders, you have this robust expansion. In non-responders, you don't. Well, where do T cell engagers or contemporary T cell engagers fall? The emerging story from hem-onc and emerging AID patient studies is they fall into the minimal T cell expansion category. And this is based upon a number of publications. First listed below is with Blincyto. Tommy referred to and others had noted. Reduced cytolytic function has been reported in ALL patients who have been treated with Blincyto. Amgen then studied the T cell expansion. They noted minimal or unchanged naive central memory effector memory subsets in these patients. So once again, reinforcing a minimal T cell expansion with Blincyto. As we start looking at the recent EULAR updates, while there's improvement in activity, evidence of activity with T cell engagers in autoimmune disease patients, it appears to be temporary. Schett and Bucci reported that looking at teclistamab in some of these patients, the naive and central memory subsets were unchanged. Once again, reinforcing that with T cell engagers, the contemporary T cell engagers, we're getting this minimal T cell expansion, and once again being overly reliant upon the existing effector population to drive the activity that we're looking for. And then finally, you can move beyond Blincyto. J&J's reported similar observations with talquetamab as well as teclistamab observed in hem-onc studies. So the key question for us was, can a bispecific T cell engager be redesigned to improve the T cell expansion as well as depth and durability of responses? We're not going to go into detail exactly what we did on the redesign today in this competitive environment we live on. What we're going to do today is we're going to share with you the underlying biology that I hope to convince you that we're driving fundamentally different biology in T cells that we believe is going to lead to fundamentally different outcomes with our ARM platform. So beginning on this slide, what we have on this slide, or the upper panel is looking at CD19 bispecifics, the lower is CD20. What we have here is we take healthy patient PBMCs, and we simply add this bispecific to drive B cell depletion. And we have the ARM in red and the T cell engager in blue. you can see we've got comparable activity with both the ARM and the T-cell engager with respect to B-cell depletion. In the middle panel, looking at T-cell expansion, interestingly, you can see the ARM is showing the desired trait. We have a significant expansion both with CD19 and CD20 arms, certainly compared to the underlying T-cell engagers. And interestingly, on the far right, we're able to do this with minimal cytokine release in this particular PBMC assay. Looking across a range of inflammatory cytokines, interferon gamma, TNF alpha, IL-6, clearly a significantly reduced cytokine release profile in this model. Sometimes we see a little bit more IL-2. We think that may have more to do with the expansion profile of that the ARM drug triggers. On the next slide, what we've done here is we've gone into a little bit more detail, trying to understand what's driving this expansion as we look at the underlying T-cell subsets. Once again, we're talking about the naive, the memory populations, the effector populations, and the colored legend is on the left. So what we've done here on this particular slide is looking at the CD20C T-cell engager. In blue is B-cell depletion, and you can see at this concentration in this particular study, you only got about 40% B-cell depletion, and it primarily occurred in day 1. If we look at the underlying memory subsets and T-cell subsets, you can see that there's minimal expansion of the memory population, nominal expansion of even the effector, and you can see actually in some cases a reduction in that. And we would posit that that's probably why you're starting to have this plateauing of activity with this drug. Now contrast that to the CD20 arm on the bottom. We ended up with full B-cell depletion occurred by day 5. But more importantly, look at the y-axis. We're talking about 22,000-fold increase in T cells. And looking at the underlying subsets, by day 5, we've got a significant expansion of the memory population. Coming back to this now serves as a reservoir of the underlying effector population that is actually driving the B-cell depletion in this particular model. You can see that we've been able to drive significant expansion and maintenance of the effector population, and we would posit that that's what's driving the difference in the activity here. Looking on the far right, the contemporary T-cell engager, consistent with the data shown on the previous slide from publications prior to us, our data would also support minimal T-cell expansion. However, the arm on the bottom is more reflective of the responding patients to CAR-T, PD-1. We're getting this robust T-cell expansion that's driving a deep, meaningful B-cell depletion in this particular assay. On the next slide, similar assay, but now we're focused on durability. So contemporary T-cell engager on the top, the blue curve is B-cell depletion. So in week 1, you can see at this dose, we got full B-cell depletion by day 7. What we then did is we added that patient's additional B cells to the T cells on day 7, day 8. And you can see in week 2, there was limited B cell depletion with the contemporary T cell engager. Once again, looking at expansion, you had minimal expansion of the memory population. Over time, you actually had a loss of the effector population. So it's no surprise that with the loss of the effector population, the inability to continually replace that effector population, that the desired B-cell depletion activity was lost in week 2. Contrast that with the arm on the bottom. You can see we've got full B-cell depletion in week 1, as well as in week 2. When we look at the underlying subset analysis, large memory population expansion leading to an expansion of the effector, but probably equally importantly, we've maintained that effector population so that we could maintain a much more durable response throughout week 2 here to drive full B-cell depletion in both week 1 and week 2. So what this is now beginning to draw together is that our arm is driving fundamentally different T-cell biology with respect to expansion of the memory, rescuing of the effector population, that's leading to a fundamentally different outcomes in this B-cell depletion assay in healthy patient PBMCs. Now what I want to move on to is our CD19 ARM program that is our lead program with a planned first-in-human phase 1 for the first half of next year. The way that we envision this working, summarized on this slide, beginning on the left, you've got your mix of B cells, including the autoreactive B cells. will provide our arm. We expect to see this expansion of T cells. It's going to drive the B cell response, that depletion response that we want. And then we expect a contraction of those T cells once the B cells have been eliminated. This is similar to CAR T. This expansion contraction is also very similar to our normal immune response. So we're very excited about being able to bring this to bear in autoimmune disease patients. Some of the underlying data, we've been evaluating this in non-human primates. What I want to point out on this slide is we're evaluating 2 doses that are significantly different. You can see in red, we're dosing at 2.5 mg per kg sub-Q. We've been able to dose as high as 100 mg per kg with sub-Q with no dose limiting issues or safety issues. What this is showing on the far left is we get single sub-Q dose shown in all of this leads to a prolonged B cell depletion. Furthermore, you have the opportunity by adjusting dose with our approach to tailor the desired B cell depletion profile. You can see the 100 mg per kg sub-Q had a much more durable B cell depletion profile than the 2.5, exactly what you would expect. As we look into the middle panel, both doses provided deep tissue B cell depletion. What we're showing here is spleen and lymph node. We've looked at a number of different tissues, and we see at both doses full B cell depletion in all the tissues that we've looked at. On the far right, looking at that memory B cell reset, what you're trying to do is you're trying to limit the memory B cells as long as possible, shown in light green and orange. Both the 3 mg per kg on the left and the 100 mg per kg sub-Q on the right, you can see the 3 mg maintained this through the last time point we had in this particular study, maintained this memory cell reset for out to 20 to 12 weeks. On the right-hand side, the sub-Q had a deeper response. You can see deeper through 8 weeks and was maintaining a nice deep reset through the last time point we had. So what I want to share with you on this particular slide is what we're providing on CD19-ARM based on this data set is the ability with a wide dosing range to optimize the desired efficacy profile. How deep do we want it? How durable do we want it? The B cell depletion to continue. We have a wide range from a low of 2.5 all the way up to 100 to do that. Because we've had no dose-limiting toxicities, presumably can go even higher. So we have wide latitude to select a dose. The only thing that then you might wonder about is, well, what about CRS? Is that going to be a limitation with this approach? It certainly has been a challenge for T cell engagers in general. So on non-human primate data shown on this next slide here, what we're sharing with you on the left, on the upper panel, is B cell depletion. The goal here is you want to get to full B cell depletion on these non-human primates as you can get. On the bottom is we're tracking on IL-6 levels at these same doses in the animals. Here, what you want to do is minimize IL-6 levels as probably one of the better surrogates for CRS risk. What we show is you can see we've done a number of non-human primate studies with our CD19-ARM, starting with doses as low as 1 mg per kg IV. We get full B cell depletion across all these doses. Going below that to IL-6, you can see nominal IL-6 at any of these doses, very, very low levels of release. All of the competitor molecules that we're showing here, when they got full B cell depletion, it came with significant IL-6 levels on the bottom, and oftentimes full B cell depletion wasn't obtainable because the animals had to be euthanized due to safety issues. So what we shared with you on these last 2 slides here is on the activity B cell depletion and tissue and durability of response, you've got the ability for a wide dosing range. What we're sharing with you on this particular slide is that dosing range is going to be selected. The dose is going to be selected based on what is the optimal efficacy profile and is not going to be limited by CRS profiles. A couple of other things. This CRS profile would be consistent with an outpatient treatment opportunity in our patients. So right now, what we're looking at going forward, sub-Q, single dose, how long does it last with the potential for outpatient given this the safety profile that we've shared with you. On the next slide, just simply looking at patient PBMC samples. You can see lupus, RA, myositis, myasthenia gravis, and healthy. And on the left hand, we're just sharing with you EC50s. You can see low picomolar activity against all of these different autoimmune PBMCs. And keep in mind, these are the assays that the FDA typically wants to see as they start thinking about first dose. So very potent drugs across all of these patients. On the right, you can see all the different patients as single dots. Full B cell depletion was achieved in all of these patients. Below that, just not going to go into great detail, but you can see similar to what we've shown previously, you get this expansion of the memory, maintenance of the effector population driving full deep B cell depletion. So the autoimmune disease patient PBMCs are behaving exactly like how we showed you that the healthy patient PBMC samples are behaving, which is consistent with our cyno data. The other thing I wanted to note just on that cyno data, we've done a similar subset analysis. We don't have it in here because it's very detailed, but at a top level, in the cyno studies that we reported, we also saw this similar expansion of the memory population and maintenance of the effector population while B cell depletion was occurring in those animals. So tying together that the arm is driving fundamentally different T cell biology that we believe has the potential to lead to fundamentally different outcomes. Clearly, our non-clinical data is already beginning to show clear indications of that wide dose range opportunity, minimum CRS profile, single dose opportunity, sub-Q, really is setting the stage for a quite compelling opportunity in autoimmune disease. Now, taking all of that data, as we're moving forward in our phase 1 study design, we're first going to go into healthy normal volunteers. This is going to allow us to rapidly understand, do we achieve B cell depletion and what is the CRS risk and how durable is that single dose B cell depletion? It's going to be a cost-effective way to get at that critical question. Assuming the data here is consistent with everything we've shown non-clinically, we will then be able to move rapidly into autoimmune patient studies based upon this healthy normal volunteer. So at this point in time, we believe we've identified a cost-effective path forward that's going to give us the key differentiation data early on, then leverage that into autoimmune disease indications. We've had dialogue with regulators about the healthy normal volunteer study. What I'm sharing with you here is consistent with all the dialogue and plans that we're putting in place with those going forward. So just at the top level, some of the key developments for both the CD19 arm and our platform. First in human dose, like I said, is the first half. Regulatory filings planned for the fourth quarter of this year. We're well into GMP manufacturing. Keep in mind, this is a bispecific antibody, FC-based bispecific antibody. We've just done some redesign of the underlying T cell engager to derive our arm. That's going very, very well. No issues whatsoever there. Our human dose projections are very low. 5 to 12 mg total dose is what we expect for this arm in humans, is what we're projecting based on our non-clinical studies. Dosing convenience, two things to think about. Sub-Q dosing coupled with lack of CRS highlights potential for community-based outpatient treatment. And as we think about T cell engagers, if we have to dose once every quarter, once every 6 months, or some interval, because we haven't seen any indications of CRS, we don't have to do that with a step dose. We don't have to do that with hospital stays potentially. Really highlights a potential for an ease of use advantage. And then the ARM platform itself, we're advancing a number of programs here, including targeting BCMA, CD20, BAFF receptor, and we're looking at trispecifics, both for autoimmune disease as well as some hem-onc settings. In addition, we're keen to understand how this works in solid tumor evaluations. It's a little bit further behind, but early indications are positive. And if indeed the underlying ARM approach works in solid tumors, we would expect to be including that in future tractors, where we would look to combine that with our tumor-activated approach. So very, very new opportunity, exciting opportunity for Janux going forward. So just in summary, we believe this is a differentiated ARM platform with a number of different advantages. We've maintained full cytolytic activity while reducing cytokines, We get the T cell expansion leading to longer duration and less T cell exhaustion. We think we have a best-in-class opportunity for B cell depletion. The data that we've shown right now, what's emerging in the autoimmune disease, what's really going to differentiate is how deep and how durable is that response. Having a close to 100-fold dosing window, and it very well could be larger than that. We don't have any dose-limiting tox at 100 mg yet, but large safety window is really allowing us to have this. We can optimize dose in a very large dose range. The durable T cell activity may also reduce risk of infection. You may think part of the reason infection risk could be occurring, of course, there's the B cell, loss of B cells, but we're also aware that the T cell dysfunction that some of the hem-onc drugs trigger in T cells, the exhaustion, some of the others, and presumably the loss of effectors, probably also contributes to infection risk. So we have a number of ways to think about this ARM program going forward. Janux itself, our team, we've got a great team, clinical group with clinical experience, a non-clinical group that's doing cutting-edge work. What's unique about Janux is we're so small. Our clinicians sit in the research meetings, understand the data. Research leaders sit in the clinical meetings. It's a continuous dialogue between those two groups, which is leading to opportunities like our tractor, our tracer, and our ARM. And then also, rapid proof to clinical proof of concept. That healthy normal volunteer study beginning next year really is going to give us a key data set that we're going to look to be leveraging in autoimmune disease studies thereafter. So in summary, potential best-in-class profile. Really, we think it has an opportunity, given this expansion profile, to potentially match the CD19 CAR T efficacy in an off-the-shelf outpatient therapy setting. So with that, I want to end today's presentation. I want to thank you all for your time and attention. Look forward to additional dialogue with many of you in the near future. So with that, we'll sign off, and thank you very much.